So today we can see supervised learning algorithms. Supervised learning algorithms are roughly speaking, they are learning algorithms that learn to associate some input with some output. Okay, that means we give some inputs that are labeled data. Given a training set of examples of inputs X and outputs Y. So we specify that for this input, this should be the output. So we have a set of data like that, and using that data, we train the system. Okay, as I said in the last class, if I want to I want to develop a system which identifies images of a flower. Okay, so in that the input will be a set of images which includes images of flowers and other than flowers. Okay, so different images we feed, and we know the output also, the y means yes or no. If I feed the image of a flower, the output should be yes, otherwise it should be no. So that input output pair we are feeding to the system, and we train it. Okay, after training, if we give any input, any labeled unlabeled data, it should be able to identify. Okay, so that is supervised learning. Supervised learning means we tell the system that whether it is correct or not. Okay, we give some input and we get some prediction from that system, and if it is wrong, we tell the system that okay, this is wrong answer, so the right answer is this one, so you have to correct it. Okay, so that kind of learning is supervised learning. And when we consider supervised learning algorithms, there are a lot many algorithms are available. We are considering only 5 of them. One is linear regression and logistic regression, support vector machine, K-nearest neighbors, and decision trees. So these are the 5 algorithms we are going to look at. And all these are simple. Most of these algorithms are very simple and straightforward algorithms. So first one is linear regression. In linear regression, it is a linear model. Linear model means that model is a straight line actually. A model that assumes a linear relationship between the input variable and the single output variable. Okay, input variables and single output variables. So here the input is a set of variables x. Okay, it's a vector, and the output will be a single value, and we call it as a y variable y, or in other words, we call them as independent variables and dependent variables. So in this is actually the input variables x are called independent variables. So they are not depending on anything, independent variables, and the output variable is called the dependent variable, because they depend. It is depending on these independent variables. Okay. So we find a relationship between we assume that there is a linear relationship between this x and y. Okay, x is a set of variables and y is a single value. So that linear relation is modeled as a straight line normally. So that is linear regression. Suppose these blue dot lines are dot points are data values that are our input values. Okay, on the x-axis we show the independent variables, and on y-axis we show the dependent variable. Okay, and we try to find out, so these are the training data. These blue dots are actually training data. For that we know the x values, and we know its corresponding y values. Okay, and based on this value we try to model it using a straight line. Okay, so this is the line of regression. So this line passing through this dark line passing through these dots, blue dots, are called the line of regression. Okay, so we find a best fitting line that goes through all these points. Okay, that goes through there are errors as well, Okay, but we find the most appropriate line, and we call it as the line of regression or the regression line. And if we get another data, another set of x values, and using this model, using this regression model, we can find out what could be its y value. Suppose my x values are this, okay, x values are this, okay, this, and I can predict the y value corresponding to this x, okay, based on my regression line. So that is a linear regression. Okay, it's representing linear model, and non-linear models are also there. Okay, but in linear regression we consider only the linear model. Okay, so that's how we predict the values. So these dot lines are actually these dots, blue dots, are actually training data. Okay, and when we get another data, we can predict the value of y based on this regression line, and this regression line should be apt, so it should represent the features of this data. Okay, that is linear regression. Then logistic regression. Logistic regression is used when the dependent variable is categorical. Okay, in this case, in this linear regression, it is a continuous data. Okay, y will be a continuous data. For example, in independent variables and dependent variables, in weather forecasting we get different parameters like temperature, pressure, then wind direction, everything, and based on that we can predict the temperature of the next day, okay, or next 3 days. So the temperature here, this dependent variable is the temperature. Okay, that is a continuous data. Okay, we can get any continuous value as temperature over here. Okay, so that is the case with a linear regression. When we come to logistic regression, it is a classification kind of problem. That means the output will be a category, either yes or no, or flower or fruit, like that. It's a kind of categorization or classification. So logistic regression is used when the dependent variable is categorical. So the output should be in some category other than the continuous day value. Okay. So to predict whether an email is spam or not, that's a classification. We classify an email into category 1 or category 2. Category 1 is spam, category 2 is non-spam. So that's a example for logistic regression problems. Then another example is whether the tumor is malignant or not. Okay, it's again a classification, yes or no. Okay, all these categorization is there. So we apply logistic regression in these kind of problems. So it's a classification. This x values are the independent values, independent variables. We call them as features, and we feed them into the system, and we find out, we classify like it is positive or negative, or happy or sad. Okay, like that. The classification can be there. There can be this two classes, or we can have more than two classification as well in logistic regression. Okay. Then in both these cases, logistic regression and in linear regression, we are actually depending upon the probabilities. Okay, probability so in logistic regression, we should have a categorization. So we need a classification into two categories. So for that we use the sigmoid function for the classification. So if z goes to infinity, so this is a sigmoid function like this. So if the z value is going to infinity, positive infinity, it is considered as 1, or it is class 1. Okay, and when it goes to negative infinity, that is to 0, it is the other category. Okay, it is class 2, like that. Okay, so we can classify like this. And the third one is a support vector machine, or in short we call it as SVM. SVM can be used for both regression and classification task. Okay, so SVM for classification and uh, regression. Okay, for both we can use. The objective of the support vector machine algorithm is to find the hyperplane in an n-dimensional space. That is the n the number of n is the number of features. Okay, so it's a classification or a regression. Okay, basically we call that SVM is a two-class classifier. We have to categorize the data. Okay, or in order to categorize or separate the data, we use an hyperplane in n-dimensional space. Okay, that distinctly classifies the data points. And to separate the two classes of data points, there are many possible hyperplanes that could be chosen. So our objective is to find a plane that has maximum margin, that is the maximum distance between the data points of both classes. Maximizing the margin distance provides some reinforcement so that so that future data points can be classified with more confidence. So suppose these are the two classes of data we have. The circles is one kind of data and the squares are another kind of data. So we have to find a hyperplane that completely separates these two categories. Okay, these two categories. So all these lines that we have shown here, these are planes that separates these two categories, okay, in different ways. So this line actually separates these two categories, and this line also separates, and this line also separates, and this line also separates, and this line also separates. So in 2D, we require only a line to separate the classes. And when we come to 3D, we require a plane to separate the classes. And in higher dimensions, we use hyperplane to separate the categories. Okay, so now we are talking about only 2D. Okay, so we have two categories. One is of a circle and the other one is square. And these are many options. We have many options for a line to separate these two data sets. Okay, and we have to concentrate on this. We have to maximize the margin distance. Okay, and so we have to find out a line that increases the margin between these two classes and from the partitioning line. Okay, so when we take this line, this is the optimum solution, optimum hyperplane that maximizes the distance or maximize the distance to two classes. Okay, so these are the margin lines. That means that goes through that is at the margin of each category. Okay, this one and this one. And we can see that some data points are there on the margin. Okay, and these data points are actually called as the support vectors. Okay, so when we take a larger example like this, we have two categories. One is a circle and the other one is a square. Okay, we can find a line like this. So if we take a line like this, the margin will be very small. Okay, the margin will be very small. The margin means a line from this our hyperplane to the nearest data point. Okay, that is this distance, and from this line to this one, so that should be equal on both sides. Okay, so when we take this line as your separating line, that will give you a smaller margin. Okay, and if you consider this line as a separating line between these two classes, we get a larger margin. Okay, we can see that from this line to the nearest data point, the margin is higher. Okay, so this is called support vectors. So the lines, the data points that are lying, that are actually lying on the margin, they are called the support vectors. Okay, so this is the most accurate line that separates these two classes. Okay, this line is also separating the classes, but the problem is the margin is very less in this case, and here in this case the margin is optimum. Okay, and support vectors are data points that are closer to the hyperplane and influence the position and orientation of the hyperplane. So based on these support vectors, we are actually adjusting our margins or the orientation of the hyperplane. Okay, using these support vectors, we maximize the margin of the classifier. Deleting the support vectors will change the position of the hyperplane, of course. Okay, so when we remove one of the support vectors, the margin will be different. So then the fourth kind of algorithm is K-nearest neighbors algorithm, and used to solve the both classification and regression problem. Okay, and for example, the classification problem is like this, that is yes or no answers will be there. So here if we have the x values as age and y values as 1 or 0, 1 means yes, 0 means no. So it's a classification problem. We give we give age as input and we get the output like here, whether that person like pineapple on pizza. Okay, likes pineapple. That's a categorization or classification. And another regression kind of problem is the output is a continuous data. Okay, so we give height as input and we get the output weight as output. Okay, it's a continuous value. There is no categorization. It's actually continuous values. But when you look at it, it gives you a classification, either 1 or 0. That's a classification. Okay, and the KNN algorithm, K-nearest neighbor algorithm, assumes that similar things exist in close proximity. So it's in case of classification we say like that, calculating the distance between points on a graph. Okay, so we it is based on this concept like Euclidean distance. So how do you find the proximity? The proximity is calculated using calculated as a distance between 2 points, or we say we used to take the Euclidean distance to find out it. Then the algorithm says goes like this. We have to first load all the training data and initialize k to your chosen number of neighbors. So we can initially we set some random value for k, and for each example or each sample in the data, calculate the distance between the query example and the current example from the data. Okay, add the distance and the index of the example to an ordered collection and sort the ordered collection of distances and indices from smallest to largest, that is in the ascending order by the distances, and pick the first k entries from the sorted collection. Okay, get the labels of that selected k entries. And if regression returns the mean of the k labels. Okay, if classification returns the mode of the k labels. So that's how that means that if we have a set of data, we say that we have to check whether it is belonging to this particular class or this class. So this is class 1 and this is class 2, and if we have a data somewhere here, we have to say whether it is belonging to this class or this class. So for that it has to take the k neighbors. Okay, suppose I take 4 neighbors and find the distance between these two and distance between these two. Okay, and whichever is smaller, I choose that class. Okay, so if this distance is smaller, if these two distances are smaller, I say this point or this data is belonging to this particular class. Okay, belongs to that class. Otherwise, if this distance is smaller, I can say that this point is belonging to this class. Okay, that is the overall idea about this K-nearest neighbors algorithm. And in the classification problem, we take the mod of the K labels. We take the mod value, and if it is a regression problem, we take the mean value. Okay, that is K-nearest algorithm, and how to choose the optimal value of K. So here I have taken it as 4. And is it an optimum value to take it as 4, whether it is correct or not? So how to choose the value of K? K is the number of neighbors. When dealing with the two class problems, it is better to choose an odd value. Okay, instead of even numbers, take an odd number as K. Okay, in my example, I have taken 4. So instead of 4, we have to take 5. Okay, that is, it should be an odd number. Then another guideline for this is the value of K must not be a multiple of the number of classes present. For better results, we have to follow these rules. That is, the K value should not be, that means I have taken 4, that's a wrong thing. It should not be taken like 4 because it is a multiple of 2. We were talking about 2 classes, class 1 and class 2. So 2 classes are there. So the K should not be a multiple of 2. It should not be 2 into n. Okay. So that is another guidance for selecting K. Then calculate, another method is to calculate the square root of n, where n denotes the number of samples in the training data set. Okay. So another option to K, so suppose you have 100 data in a data set, we take 10 as the neighbors. Okay. So that is another method to choose K. And in any case, K should not be a lower value, such as K equal to 1 or K equal to 2. Okay, if we take like that, it will be resulted in overfitting. Okay, so we should not go for that lower values. Then the last one is decision trees. In decision analysis, decision trees can be used to visually and explicitly represent decision and decision making. It covers both classification and regression problems. Okay, decision trees, in classification we use classification trees, that is the yes or no types. What we have seen in an example. So okay, we see the example in the next class. So the classification can be like a fit or unfit. It's a category kind of output. And in the regression trees, the output will be continuous data. In the outcome will be numbers like 1, 2, 3. Okay. So this is a structure of a decision tree. There is a root node. It's a root at the top. Okay, it's a root node. And the root node is splitted into 2 subnodes. Okay, splitting like this, decision node and decision node. And this decision node again divided like that. Okay, and it will end at the leaf node, we call it as terminal nodes. Okay, so when you consider it decision tree, it has mainly these 3 kind of nodes: root node, decision node, and terminal nodes. Okay, and root nodes, it is a node present at the beginning of a decision tree. From this node, the population starts dividing according to the various features. Okay, the decision trees are actually the features we talk about. The nodes, decision nodes, the nodes we get after splitting the root nodes are called decision nodes. Okay. Then leaf nodes, the nodes where further splitting is not possible. They are called the leaf nodes or terminal nodes. And the subtree is just like a small portion of the graph is called the subgraph. Similarly, a subsection of the decision tree is called a subtree. So that's what shown here. Okay, so mainly in a decision tree, we have 3 kind of nodes. One is root node, the other one is leaf node, and in between we have the decision nodes. The decision nodes decides whether it has to be split more. Okay. Then another terminology we use here is pruning. Is nothing but cutting down some nodes to stop overfitting. Pruning means we are cutting down the trees. Okay, the branches of the trees. So this is an example for a decision tree. We have to check whether the weather correct today's weather is cloudy or windy or humidity. Okay, so that the three categories we have here. So this is if it is sunny, we call it as we go to the decision humidity, whether it is humid or not, humidity is high or normal. Okay, yes or no, we have to take. Then if it is rainy, the wind is strong or weak, we have to take. Why didn't we split more? Okay, or why did it stop there? So we have to find out when to stop this splitting. Okay, we goes on splitting like this. That is a decision node, and here we got a terminal node, and here we have another decision node. So how long we can go deeper in this decision tree? So how do we find it out? Okay, and we find this depth of the tree or how long we have to split, that is based on the parameters entropy, information gain, and Gini index. And what should be the root node and what should be the decision node, and when should I stop splitting? To decide all these things, we should know the entropy, okay, which is the amount of uncertainty in the data set. Okay, so the entropy is nothing but the uncertainty in our data set or measure of disorder that you might have heard in mechanics also. Entropy is the measure of disorder actually. And this is the formula for finding out it. P is the P plus and P minus is there, and P plus is the probability of the positive class. Okay, then P minus is the probability of the negative class, and S is the subset of the training example. So E is the entropy, of course. E is the entropy of the subset is equal to minus of probability of the positive class into log P minus P of the negative class into log P. Okay, so this is P of the negative class. So this is the equation we follow in entropy. Then a pure sub-split means that either you should be getting yes or you should be getting no. Okay, if in that case there is no more splitting. Like this. So when we start with the yes or no, 8 yes is there, 4 no's are there. So of course we cannot decide. Okay, so we one of the option we got is 5 yes and 2 no's, and another option is 3 yes and 2 no's. Okay, and here also we cannot 5 yes and 2 no's. Here again we cannot decide whether it is yes or no. So we again split like this: 5 yes and 2 no's, and 3 yes and 2 no's, like that. Okay, and when we get the single answer yes or no, we stop the splitting. And information gain, the goal of machine learning is to decrease the uncertainty or impurity in the data set. Here by using entropy, we are getting the impurity of a particular node. We don't know if the parent entropy or the entropy of a particular node has decreased or not. Okay, so the entropy is talking about a single node, and information gain says that by dividing a node into subnodes, whether the entropy getting reduced or increased. Okay, so the information gain is the measure of finding out the overall entropy of the node, okay, or the data set. For this, we bring a new metric called information gain, which tells us how much the parent entropy has decreased after splitting it with some feature. So information gain measures the reduction of uncertainty given some feature, and it also deciding factor for which attribute should be selected as a decision node or root node. Okay, the information gain, this will tell you which is the feature for which we have to split the node once again. So information gain is calculated like this: EY minus Y given X, or in other words we can say that entropy of dataset minus entropy of feature. That is information gain of the feature. Then Gini index, it is calculated by subtracting the sum of squared probabilities of each class from 1. It favors larger partitions and easy to implement, whereas information gain favors smaller partitions with distinct values. Okay, a feature with a lower Gini index is chosen for split. Gini index is calculated like this: 1 minus sigma p of x equal to k to the power 2. Okay. So these are the equations we just go through. Okay, we are not going into deeper. And when to stop the splitting, in order to find out this, we can use some methods, that is minimum sample leaf. It represents the minimum number of samples required to be in the leaf node. The more you increase the number, the more is the possibility of overfitting. So we have to find out the minimum sample leaves in the nodes. So in the tree. Okay, so it should not be larger. If the leaf nodes are larger, there are chances of overfitting. And the maximum features, it helps us to decide what number of features to be considered when we look for the best split. Okay, then pruning, it helps in improving the performance of the tree by cutting the nodes or subnodes which are not significant. Okay, pruning is actually trimming down the tree. Trimming based on the significance of the nodes or subtrees. It removes the branches which have very low importance. Okay, that is pruning. And pre-pruning and post-pruning are there. Pre-pruning means even before constructing that branch, we cut it down. Okay, we can stop growing the tree earlier, which means that we can prune or remove or cut a node if it has low importance while growing the tree. So we do not allow the branch to grow in that direction. Okay, that is pre-pruning. And post-pruning means we first allow the tree to grow in full strength, and after growing, we cut down some of the branches. Okay. Once our tree is built into its depth, we can start pruning the nodes based on their significance. So that is pruning. Okay, that is all about the supervised machine learning algorithms. Okay, the first one was a linear regression, then logistic regression, then support vector machine, Knearest neighbors, and decision trees. Okay.